Okay.
Yeah.
All right, good. So let's we're going to look more at exponential functions. So who remembers what an exponential function is? Where will you find the variable? Like the x.
You'll find it on
It's in the name. It's up in
the exponential.
It's up in the exponent. The variable would be up in the exponent,
yeah.
right? Okay. So we're going to look at some basic exponential functions and kind of graph these things here. So we have an exponential function here, basic form y equals b to the x. And notice they say here that b is greater than 0, whatever number it is, and b is not equal to 1. Okay? Because if it's 1, then really all you have is a straight line, isn't it? Because 1 to any power is just 1, yeah? But what about b greater than 0? What's another way to think of that? If some number is greater than 0, what else can you say about it? That number is what?
That means that there is no negative number.
Okay, so in other words, the number will be not negative.
Positive.
There we go. So if you see greater than 0, that's another way just to say positive mathematically, right? All right, so let's look at this function down here. Y equals 2 to the x. So 2, right, that's the base of this function, right? And then x is up in the exponent. So we're going to make a rough sketch of this by doing a table of values. You've done this with, other functions, linear and quadratic and maybe parabolas, okay? So how fast do you think this function will grow? 2 to the x power. Like as x gets bigger and bigger, will it grow at the same rate all the time? In other words,
Yes.
So you think it'll be a straight line?
No, it would be more like
So like every time you apply a bigger value of x, it's going to get exponentially larger, right? Let's do the table of values here then, okay? So 2 to the x, right? So if we start with -3, right, we'd have 2 to the -3 power, which is really what?
1/8.
1 over 8, right? Not making anything negative. Please know that. Negative exponents don't make anything negative, okay? All right, so let's do an x of -2. So that would be 2 to the -2, which is really 1 what?
4.
1/4. 2 to the -1 would be 1/2, right? Are my numbers right now getting bigger or smaller as we go?
Bigger.
1/8 is the smallest of those, right? 1/4 is bigger, half's bigger than a fourth, okay. 2 to the 0 power is what?
1.
1, good. And then, of course, 2 to the first is just 2. 2 squared is 4, right? And 2 to the third is what? 8. Okay. So let's plot these points here, right? So we have -3, and we'll have to just kind of estimate 1/8, right? So if we go 1, 2, 3, up about 1/8, pretty close to that line, isn't it, right? And then -2, up about 1/4, yeah, maybe a little off. -1, about 1/2, right? And then at 0, we're right at 1. Hey, that point I just put on there, what's another name for that point? For the graph. Is that where it crosses the y-axis? What do we call that?
The
y
y-axis.
intercept.
Y-intercept. Yeah.
Okay. So let's keep going there. So we have an x of 1. Our output is 2. An x of 2. We're going up to 4. 1, 2, 3, 4. Right? And an x of 3. We're going up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So does this look like it's climbing at the same rate between every point?
No.
It's considerably larger, isn't it? So let's just kind of sketch a curve through here like this. I missed a little bit, but that's okay. So this will be the graph of y equals 2 to the x. Okay? And that's what an exponential function looks like. And that would be called exponential growth. You've probably heard that term out in the world, right? And this is what it means. So like at every step, it grows faster and faster and faster, right? So it's not linear. It does not have a constant rate of change. That rate of change keeps changing, doesn't it? Okay. And by the way, when the graph here goes this way, do you think it will ever reach zero? I mean, it keeps getting smaller and smaller. Do you think it'll ever reach zero?
No.
It won't, right? And so what we have here on this axis, I think you've heard this term before, right? Is called an asymptote line, okay? This is called an asymptote. Right? And this is a line that your graph, your function will get like infinitely close to, right? But it'll never actually reach zero. It never reaches zero going to the left. And we'll look at that a little more here in a minute. Okay? Gets closer and closer and closer. Right? Okay, so any questions on how to graph? That's what an exponential growth function looks like. Okay? And notice that this here, this base, this b, is greater than 1. Okay, and the graph goes up very quickly. Let's go look at exercise 2. You know what, this should have parentheses around it, so the whole 1/2. That's a little typo there. Let me make a note of that. Right, because you want that whole thing to be to the x power, right? So let's think about 1/2 to the x. Let me just do this. See note. Let's go to our notes page real quick. I just want to run something by you here. Okay. 1/2 to the x. Let's think about this function for a minute. Okay. Let's try 1/2 squared. What do we get? That's 1/2 times 1/2, isn't it? And what is that? 1/2 of 1/2 is what? 1/4, right? Let's try 1/2 to the third. That's half of a half.
That'd be 1/8.
1/8, right? How about 1/2 to the fourth? 1 double the 8.
1/16.
1/16, right? And if we do half of that again, or in other words, 1/2 to the fifth, we're getting 1/32, aren't we? Right? And keep going, 1/2 to the sixth, 1/64, right? So it keeps getting smaller and smaller and smaller, doesn't it? Will this ever reach zero?
No.
No. So this function, doesn't matter what the exponent is up there, right? It will never reach zero, right? And that's what we call an asymptote, okay? So this is important to know. It has an asymptote line. So it's like the classic mathematical question when you're looking at these exponential functions that are less than 1. Let's say you want to walk across my classroom, right, to one of my walls, okay? And I tell you, okay, walk halfway to the wall, right? So the wall's what? Like, let's say my wall is 20 feet from you, and you walk halfway. How far are you from it when you walk halfway to it, if it's 20 feet to begin with? What's half of 20? 10 feet, right? And then I say, now go halfway closer again. How far are you from the wall?
5 feet.
5. Go halfway closer again.
2.5.
2.5, right? And so on and so forth, right? Will you ever actually hit the wall if you keep doing that method? Half, half, half. No, you really won't, right? Because there's an infinite number of fractions and decimals, aren't there, that you can reduce to? Does that make sense? That's what it's known as uncountably infinite. But you don't have to remember that. But like in a practical sense, you will get close enough to the wall to say you're at the wall, right? But in the theoretical sense, you will not actually hit the wall, okay? So let's go back here, and we've actually done some of these values here. So let's do a table of values for y equals 1/2 to the x. Well, we already did -3, right? So it would be 1/2 to the -3. We know that's 1/8, right? And then 1/2 to the -2, of course, is what? 1 over or guys are so slow. 1/2 to the -1 is what?
Would be 1/2.
Oh, to the negative. You know what? Jeez, I'm doing this. I'm sorry.
Yes.
Yep. No, I was. Heck, sorry. Sometimes I'm too smart for my own good, and they start thinking ahead to other things and writing down what I'm thinking ahead about. Sorry. 1/2 to the -3 is actually what?
Be 8.
8, wouldn't it? Okay. Sorry about that, guys. That's why we do math in pencil, right? And then 1/2 to the -2 would be 4, wouldn't it? And then 2. And then what's 1/2 to the 0 power?
1.
1. And then 1/2 to the first is, of course, 1/2. And then 1/2 squared, you know, is 1/4. And then 1/2 to the third is 1/8. It's like half of that again, right? So let's plot these then. So now we have -3, 1, 2, 3, 1, 2, 4, 5, 6, 7, 8. So -3, 8, right? And then -2, 1, 2, 3, 4. And then -1 is up 2. And then at 0, we're at 1. What's this point called where I just hit the y-axis?
Y-intercept.
It's the y-intercept. And what's the value of x at the y-intercept?
0.
0, all right? Always the value of x at any y-intercept is 0. And so we got 1, 1/2 about there, and then 2, 1/4, and 3, 1/8, right? Are we ever going to hit that x-axis?
No.
No, it's like walking halfway to the wall at every step, right? It's, you know, like if you're using this function to do something in engineering or, you know, physics or design something, you'll all have to decide as a group of engineers how close is close enough to say you're at that 0, right? But it will never actually. So again, we have another asymptote line. This is the line y equals 0, and that's our asymptote. It will never actually reach that. Okay? It will never actually reach that. So our first function there up in exercise 1, that was exponential growth. Everyone would agree, right? Because up here, as x is getting larger, what is y doing?
Y is always getting higher.
Getting larger, right? But down here, this is not growth, right? Notice we have this fraction of 1/2 to whatever power. This is called exponential decay, right? So this is decay. And I'll go ahead and put the other one up here. This is up here is growth, right? Exponential growth. And they're both very common functions actually out in the real world. Has anyone taken chemistry yet?
I think it next part period.
Okay, so I think in chemistry you'll talk about like a radioactive half-life, right? Like how long until half of some substance is decayed, right? And that's exponential decay, okay? You start out with a full amount of substance. At some time you've got half of it left and then half of that left, right? And this will be a graph of that, okay? All right, let's go over to the next page. Let's talk about the domain and range of some of these things. All right, remember the domain is what values? All the what? X or Y? X. And the range would be all the Y, or the output values, right? So over on the next page here, exercise 3, based on the graphs, maybe saw 1 and 2, state the domain range for an exponential function in this form, y equals b to the x. Well, what about the domain? Are there any x's that we cannot use?
We cannot use any that we can use everyone.
Yeah, we can use any x, right? So x can be any real number, can it? From negative infinity to infinity. Yeah. So we could say, like, that set would be all x such that, well, there's no restriction on x, right? So we could just say x, if you remember this, is an element of the real numbers, right? Without any restrictions, okay? Or another way to say this would be all real x, right? What about the range for y equals b to the x?
It cannot go lower
Then what?
than 0.
Zero. It will never reach zero, right? So
Yeah.
our range, our y's, right, would be all y values such that y is what? What's the restriction?
Y is more than 0.
Okay, greater than 0. Greater than or equal to? Or just greater than?
Greater than.
Greater than 0, right? Okay. So this refers to our asymptote, right? Y is always greater than 0, okay? Because again, you walk halfway to the wall and then halfway again and halfway again, and theoretically you will never get to the wall, all right? But again, in a practical sense, you can decide, you know, how close is close enough, right? Is 1/64 of an inch close enough, Mr. Hepper? Yeah, I think that's good, right? You're there. But theoretically, you won't. Okay, so exponential functions are 1 to 1. Remember that? Like every input and output are distinct numbers, right? Nothing really repeated in the inputs and output. How can you tell? What was the test for 1 to 1?
Horizontal line test.
Yeah, and do they pass the horizontal line test?
Yes.
So yes, they passed the horizontal line test. If we went back to the other page and did that. Okay. All right, let's go on to exercise 5 here. We have a function y equals 7 times 3 to the x. What's the base of our function here? 3, right? 7's not the base, it's just thrown in there, right? Gonna make it climb a little bit faster, isn't it? So let's determine the y-intercept. Where do we find the y-intercept, guys? Where x is what?
X equals x equals 7,
0.
0.
The y-intercept is always where x equals 0. So let's plug a 0 in for x and see what we get for the y-intercept. So we get y equals 7 times 3 to the 0. But what's 3 to the 0?
1.
1. 7 times 1, so that's 7, right? So what are the coordinates, the x comma y of our y-intercept? What comma what?
0, 7.
0, 7, right? And now, the next question is, does this exponential function increase or decrease? What's the base?
The base is 3, so it will increase.
Yeah,
the
right.
number.
If the base there is greater than 1, it's always going to increase. Right? We call this growth, exponential growth, right? If it's in that form. In part C, they want us to make a rough sketch of this, okay? Well, we know what the graph will look like, the shape of it, right? From the page before. And what else do we know? Do we know another point on this graph? Do we know another point on this graph?
Yes,
What point?
0, 7.
The y-intercept, right?
Intercept.
So let's just put, we don't go too high, so 1, 2, 3, 4, 5, 6, 7, right? So there's our y-intercept at 0, 7, and you would all agree that this graph would just roughly look like this, right? Never actually reaching 0, right? we didn't do table values, you just want to kind of a rough sketch there, okay? Any questions on this one? All right, let's go down to the next example. Now we have y equals, and again, these should have parentheses around it, so the whole thing, 1/3 to the x. Is this one going to be growth or decay, kids?
Decay.
Okay. And also, we have this +4 tacked on to the end. What do you think in part A, adding that 4 will do to the graph?
It would mean that y-intercept will be 4.
Maybe, but in general, which way would the graph be shifted?
It would shift growth, increase.
Well, it'd be shifted up 4. It'd be like,
To the right.
huh?
It'll shift to the right.
Well, all right, let's think about it without the +4 for a minute. Right? And you know it's going to be kind of like this, right? But then we do +4 to every value in the table of values. What do you think that'll do to the graph? Want to just shift it up 4 to make everything 4 larger than what it normally would be? And so shift it up? Right? Okay. I'll answer my own question. Right, Mr. Hefner. Okay. So it's going to shift it up 4. Everybody agree with that? We'll get to the left right stuff another time. But adding 4 at the end, it would shift up 4 units. Will that change the asymptote for this?
Yes.
It would, right? Instead of the asymptote being y equals 0, what would you think it would be? If everything got shifted up 4.
It would be y equals
4.
5.
4.
4, yeah.
If you shift up 4 from 0, it's going to be 4, right? Okay. So let's go to part B. Determine the y-intercept, right? Again, the y-intercept is found where x equals what?
X equals 0.
0. So let's do that. So y equals 1/3 to the 0 plus 4. What's 1/3 to the 0?
1.
1 plus 4, which equals 5, right?
5.
So our y-intercept is at 0, 5. Everybody agree with that? And they want a rough sketch of this. So let's plot the y-intercept at 1, 2, 3, 4, 5, right? And we know, you don't have to write this, right? The graph's going to do this, right? But where will the asymptote line be for this one?
It would be shifted up 4 units.
So instead of being down here at 0, instead of never actually reaching 0, it's never going to actually reach y equals 4. So your graph is going to roughly be like this, if that makes sense, right? So our new asymptote line is at y equals 4. It will never actually equal 4. It'll get really close, right? Without the +4, it would get really close to 0 and never reach it, right? But if we shift it up 4, then it's the value of 4 it'll never reach, right? Does that make sense to everybody? Okay, so we have exponential functions, that we have growth and we have decay. So if your base is greater than 1, right, the b, what do we have, growth or decay? Growth. And if the base is between 0 and 1, you know, like 1/3 or 1/2, what do we have?
Okay.
Decay, right? Because at every point, every x value, it's a fraction of a fraction of a fraction of a fraction. You keep multiplying fractions and they get smaller, don't they? Okay? All right, so any questions on exponential functions?